Hello, hi everyone. So, welcome to this module of your IoT course on IoT Security Engineering. And we'll be dealing with the cryptographic fundamentals for IoT Security Engineering. So, this book chapter, you can say, or this course chapter, this course module is primarily directed for IoT implementers, those who are developing some sort of IoT devices, networks, either for consumer or their industrial, or just are involved in IoT communications for their projects, startups, enterprises at all levels. So this is like a fundamental topic which we have to address about the security engineering. And here we will try to provide you with all sorts of information, the prerequisites which are required for having a very applied cryptographic and cryptographic implementation strategies on your IoT devices. The target audience will primarily be the IoT device developers, some security practitioners. In fact, we'll try to deal with some concepts of enterprise IoT integrators and industrial IoT implementers. So, what we're going to cover, we'll come back to this later, but just first of all, get to this critical context. As I said, that will be most of you might have seen a course and might find all this information to be common sense, what I'll be saying. But yeah, it's a given the vast spectrum of the students which are attending this course, it's important that we deal with this background topics of applied cryptography, cryptographic implementations, because even a small mistake which can be avoided at the level of any company making a consumer grade IoT device can ultimately lead to a harm of their customer if they are not careful in this. So this is the growing risk now. Uh, Covering what we'll be doing in this entire session, not in this particular video, the series which we'll be looking at. So cryptography and its role in securing the IoT. Then we'll be going over through the types and uses of cryptographic primitives in the IoT, cryptographic module principles, cryptographic key management fundamentals, and future proving your organizations or your IoT projects rollout of cryptography. After this, we'll be looking at some of the critical aspects like the public key infrastructures and the IoT identity and trust management. So this video is going to be very important and will serve as like a prerequisite for the next topics which are going to come. So let's understand the cryptography and its role in securing the IoT. So our world is witnessing an unprecedented growth in both how the machine connectivity is over the internet and private networks, and the software companies, the AI companies are playing with our data. So naturally, it becomes very important that how we are maintaining a personal privacy, and this personal privacy has been picked up by uh, governments as well, that how we can ensure that all these AI companies which are there, how they're not infringing upon all the data which is out there. There are certain laws, compliances regarding all the things. So what we see here in this is that uh, it is very important with this connected world that there are certain cryptographic primitives which are there, and then there are protocol layers and protections which will help us actually implement the IoT cryptography. And what will be the components, the modules and the keys which will be involved, and how we can, future proof ourselves for all this. So as I was telling that they play a never ending game of cat and mouse with the security industry, always trying to catch hold that okay, who is committing what crime, what are they recording. And you might see that many times Google CEOs, Meta CEOs, they're being called to the court in order to identify what all data they are storing and how they are influencing the people. So we are all victims in one sense, either directly as a direct result of a security breach, passwords getting stolen, or something getting, some data information, visa card, etc., getting leaked, or indirectly through the costs we incur to improve, the insurance risk mitigation measures, etc. So yes, the uh, security and privacy are both gaining traction in the corporate boardrooms that they want to follow those compliances and high level government circles. And therefore, all this makes understanding this aspect of IoT, the cryptography aspect, very essential. So, whether it is wireless edge network, uh, either point to point or like wirelessly, or gateway traffics, either it is backend cloud databases, software, firmware images, exabytes of your data at rest. All this is requiring security by default, like the security principles. So whenever we talk about any protocol, any security principle, there are four pillars of security. And whether the data is in transit or at rest, we have to ensure these four things. So first is confidentiality, which is encryption in itself. Primarily, no one else can read our data. Only the person whom the data is intended for can do that. So this is confidentiality, the topmost one. Then comes the authentication, that okay, maybe whatever data is coming, I'm only able to read, but whether the sender who has sent it is the actual the person from whom I'm supposed to get that message from. So that is authentication, and that is handled by digital signatures or message authentication codes. So these days you have seen that there is something known as DSC. It's very famous, digital signatures. Even Adobe or any PDF editor tool gives you option to actually sign that document with your private key. And these days, online signing of documents have also become quite common. So whether that person has actually signed the document or not, that can be ensured via the authentication thing. Third is integrity. So, what does integrity tell us? So, integrity tell us that whatever content we have received, that is exactly the same. Like one sender has sent this information and it is encrypted, but whether the information was changed in between or not, that is ensured by integrity. And finally, non-repudiation. Non-repudiation ensures that once a message is sent, the person who has sent that message, following the confidentiality, the authenticity, and the integrity, he cannot deny that he has sent that message. So there is no dispute on the message once it is sent. So these are the four pillars of security. Together, these pillars ensure the information assurance context. So this information assurance context is given by these four pillars. And yet there is another fifth pillar called as availability. Availability is something which is so common, like quite a common sense, that if you're sending an information, it must be sent first of all. So that availability uh, can be denied if in a poorly implemented cryptographic instance, the availability itself might become an issue, which you'll see that when we go to IoT devices, sometimes the information is not sent only because of certain optimizations which you wanted to have. So all these information assurance context help us avoid the risk, like help us in risk mitigation. And the risks can be at the level of host security, where the person who is sending the data, his data is itself, like his computer itself, compromised. Then about the information, like what information we're sending, mitigating that risks. And the ones which are involving sort of like a communication protocol. So we have to ensure that not only the data which is getting sent is secure, but the underlying communication layer, which is, or the protocol which is supporting that data transfer, that is also secure. So there is one real world application, the FFA case study, in which the author Van Duren spent time describing about the security needed in piloted drone communications. So the objective was that there is a prerequisite to safe and secure integration of UAVs into the national airspace system. And how he approached this was through a detailed characterization of common information types which have to flow, and the communication flows between the pilot and the aircraft. In fact, what they tried, what any UAV should support is a very lightweight authentication protocol. And when we're trying to go lightweight, it does not mean that we compromise the security aspects of it. So it is like trying to find an optimal algorithm which gives the best of the both places. So when people think about cryptographic primitives in the IoT, so immediately their mind just goes to encryption, that they have to understand a data that is scrambled so that the unauthorized parties cannot decrypt and interpret it. But the real world cryptographic complexity, as we discussed, is much more than this. It involves all these confidentiality, authentication, integrity, and non repudiation. And for this, for achieving all this information or assurance objectives, we should actually look at the some cryptographic primitives. So, as just like an implementation warning that this should only be seen by some security professional who is well versed and protocol design experts, and even the minor error can present prevent the security objectives from being fulfilled. Either four of these, if any one of them is failing, then the whole cryptographic algorithm is failing. So there are cryptographic primitive categories which are there. Obviously, the most famous one being encryption, and along with encryption, there is always this decryption which is there. Now, this ensures confidentiality. There are two types of encryption: symmetric and asymmetric. We'll go through them later. Then comes hashing. So hashing is something which we'll be using along with the combination of encryption, decryption, signatures, etc. So that is one another primitive which is very important, hashing. Then comes digital signatures. So these digital signatures, they provide integrity, identity, and data origin authentication, as well as non-repudiation. So these digital signatures are also of two types: symmetric and asymmetric. In symmetric, this MAC is used for integrity and data origin authentication. And in asymmetric, we use elliptic curves and integer factorization cryptography called as IFC. These are different techniques. And then there is another primitive which you'll see in most of the common algorithms out there related to cryptography is random number generators. The basis of most cryptography requires that which we have very large numbers originating from a high entropy source, which is basically nothing here, random number. These are needed to generate or establish cryptographic keying material and ensuring that things are at random and people's keys, whatever are getting generated further, are different, unique. So these all these security things which you'll be seeing, they're not like isolated. Like they're not used in isolation. It provides an underlying security functions for all the upper layers of the OSI stack, your communication and other protocols, including Bluetooth, Zigbee, SSL, TLS, various other protocols. So whether we talk about message protocols, message encoding, relevant protocol behaviors, etc., all these cryptographic primitives will be used. All right, now let's start discussing about encryption. So, encryption protects us from eavesdropping, and as many of you are familiar, that it is used to scramble or mask the information so that unintended parties cannot read or interpret it. Now, the primary purpose obviously is going to be confidentiality protection, that it protects confidentiality of information from eavesdroppers. They're not able to see what information we have, and allows only the intended parties to decipher the data. Now, in this also, the like the scenarios, observing your communication, attempting to read stored data. So even if someone is just observing that where the information, what to where the information going, and not making sense of that information, that is also like a security breach. So he knows these two people are communicating. What they're communicating, he does not know. But that is also potential eavesdrop security scenario. And obviously, like if he's able to read the data, it is even worse. So encryption algorithms can be symmetric or asymmetric, and we'll explain them in the next section shortly. And in both the cases, the cryptographic key and the unprotected data are used as an input to the encryption algorithm, and that encrypts the confidential information. So this is the plain text, which is the unencrypted text, and this is known as the ciphertext, the encrypted message. So whenever any encryption is being designed over an IoT network, the system security engineer needs to do a threat modeling that, okay, do I need to, is my communication channel between these two points are secure or unsecure, ins insecure? And this is like, known as point to point. And this, if like, IT device and IT device B themselves are making the decision, then it is known as end-to-end encryption, end to end. So many encrypted protocols operate only on point to point basis, like they ensure that the communication channel, uh, that whatever the communication channel is, that itself has to be secured, and what is the threat model for that. So in here, like if you're using some other infrastructure, so as an example, like if you're there on an OSI layer 2, which is called as the link layer, and there is an encryptor which may encrypt the routable network layer traffic, all the traffic which is above it, and it just ensures that when it is routing the traffic, the protection terminates at the end of the link, but the communication between the link and the device, actually that is also not secure. So basically the link encryptor is doing its job of ensuring that it reaches from one link to the other another link securely, but then the IoT device themselves have to make the decision, okay, am I securely connected with the link or not. So therefore a network encryptor which will encrypt the payloads themselves, like this thing is adding a security on top of it, definitely, which is ensuring, but the IoT device themselves will also say, okay, let me also encrypt the payload before sending it to a network routable, like before sending it to the network router. So this is known as end to end or machine to machine encryption, and this is also used. So now let's look at the symmetric encryption. So in symmetric encryption, what we do is that both the sender, the encryptor, and the receiver who is be decrypting use an identical cryptographic key. The same key is used by encryption and the decryption, and like this is the ciphertext which you see here. And yeah, some of the important properties of symmetric is that it's a reversible operation, and same algorithm is used for both the encryption and decryption process, and it is mode dependent behavior. Mode dependent behavior means whether we are doing encrypt mode or the decrypt mode, depending on that, the algorithm will change. It will use the same key, but how we are doing the reverse operation, that will change. So many times, when device A is sending to device B, they use key X, and both parties have the key X shared originally, and if device B is sharing to device A, then both have key Y, which it is already shared with them, so they both maintain key X and key Y with them. So there are popular algorithms for symmetric ciphers, including the advanced encryption standard AES, then there is blowfish, then there is DS and triple DS, then there is twofish, cast 128, camellia, and idea. So all these are their algorithms. Here, if we'll not go into much of the mathematical details of AES, DS, because that is an entire course in itself. Like if we start discussing how these things are there, we have to understand from a broad perspective what uh, what requirements are there in the IoT world for implementing the symmetric key algorithms. Now, once we discuss the different algorithms, like I'm not 100% sure whether we're going to, how much we're going to go in the next video, but at least we have to be aware of this fact that there is an initialization vector. Now, there is a common problem. See, like you have to open up your mind that it's not just sufficient to encrypt the data, but also hackers can try to extract different information from different aspects of your communication. So what happens is that let's say every time you are given an information, I'll just go back to this, that every time the information, whatever the same information you're sending and the same key you are using to encrypt that data, if there is a hacker in between, like I'm not sure how to draw the hacker, but if there's a, it's like they have this sort of a hat, yeah. So if the hacker is sitting in between, then the same information which is going and getting encrypted, every time this information is going, if the key is not changing, the same thing the hacker might be able to see, okay, this thing got transmitted, this thing got transmitted, this thing got transmitted, perhaps this is what it means, etc. So so what I just described to you was is a, like very basic cipher operation, and it is called as electronic code book, ECB mode. in which there is just one block of plain text and ciphertext at a time, and no initialization vector is required. What initialization vector does is that after every successive chunk of plain text and ciphertext data, how to modify the key, how to keep rotating the key, etc., to maintain that, like, the same data getting transmitted over the channel is appearing different over the encrypted, like, over the communication stream here. So as obvious, this thing is very rarely used in practice, and the vulnerability, as I highlighted, is that a given plain text encrypted with the same key will always produce a consistent block of ciphertext. So the risks are that it renders encrypted data vulnerable to catastrophic traffic analysis. Now, traffic analysis is a keyword here. So in order to avoid this sort of limitations which we discussed, the vulnerabilities which we discussed, there are block chaining methods. So block chaining, this is different from blockchains. And in block chaining, what happens is that there is an initialization vector. So what you do is you bootstrap the entire system with an initialization vector, which is XORed. So IV is XORed with the first block of plain text. And this plain text, whatever this result is, I'll call it as um yeah, R1, let's say. Now this R1 is sent directly, like, whatever this plain text, this XOR combination is of this plain text. Once we XOR this is sent to the ciphertext and to the scheme AES or whatever, and we obtain the first block of ciphertext. Now whatever this XOR operation, this middle point which we have, this ciphertext, we've got this ciphertext. The image here is slightly misleading. So what happens is that whenever you obtain the ciphertext, you take the next block of P2, this P2 which is shown here. So just ignore this diagram. So this P2 and this thing is again XORed. So now this becomes sort of a new initialization vector, and that is how the process continues. That you take the XOR of the result, you get the cipher, and you get the first block of your encrypted ciphertext. Now you take the previous ciphertext block and XOR it with the next plain text box, and you obtain something which is known as R2. Now R2 you send to the ciphertext again, and you obtain, so this is C1, this is C2, and then you take, so C1 XOR with P2. So this was P1, the plain text one, P2. Now you take C2 and you XOR it with P3, and whatever R3 you're getting, you encrypt that using AES and you get C3. So now what we ensure with this is two identical blocks of plain text will not have the same ciphertext representation. And this ensures traffic analysis, um, like ability to discern plain text from ciphertext is far more difficult for adversaries. Still, like, they can back calculate, try to backtrack, but it's very challenging and difficult and computationally expensive. So cipher feedback chaining, this is CFB, and output feedback modes. So depending on, like, what the mode is, each variation is, like, where IV is initially used in the as a placeholder, but depending on which mode you are operating in, either you use plain text or ciphertext, and for your zoring operation, like what you're using here, that will change either if it is ciphertext or the output text. So the pros and cons of this are, like, it prevents simple traffic analysis methods, dictionary word frequency attacks become ineffective, identical plain text box have different ciphertext representations. Disadvantages are the error propagation. So data errors, like bit flipping in RF communications, propagate downstream. Like everything, all the entire thing will get, like, it's not just one ciphertext which will get corrupted. All of it will get corrupted. So if first block of large message M encrypted by AS in CBC mode is corrupted, all subsequent blocks of M would be corrupted as well. So for this, we use stream ciphers, and they do not have this error propagation problem. The real world usage of CBC is seen in the Zigbee protocols. So in order to, like, avoid this downstream um, error propagation problem, we have this counter modes with us. So what happens in the counter mode is basically, yeah, the plain text is not directly encrypted with the cipher and key. Each bit of plain text is stored with a stream of continuously produced ciphertext. Now it's not just a single ciphertext, it's like a stream of ciphertext getting generated using some algorithm. And that ciphertext stream consists of encrypted counter values that continuously increment. So it is of two types, the counter mode and the Galois counter mode. So just what is important for us is that in the wireless communication, CTR mode is frequently used because it can do the containment of the bit error what we saw earlier. So bit errors that happen during transmission do not propagate beyond a single bit. And the important is the contrast with blockchain modes where the error propagates. More you can see some animations on this, it will be helpful, but we'll proceed from this point. So let's discuss about the asymmetric encryption. In asymmetric cryptography, so whatever the IoT device and IoT device be, they both have a public key attached to them and a private key, and these two keys are mathematically connected to each other. So every device which is like the device has its own private key with it. So IoT device A has its private key and IoT device B has its private key. And then whenever we want to encrypt an information which can only be decrypted by the device B, what we do is we take the device B's public key, which is shared on like let's say certification authority, etc. We take the secure public key of the device B and we encrypt our information, whatever we want to do using this public key. We encrypt it and we send the encrypted data. Now, no one else other than the device B can decrypt this data because only device B itself has the private key attached to it. So only device B can decrypt this data. So only of the private key can decrypt. So let's just see this process. IoT device A uses IoT device B's public key to encrypt to device B. IoT device B uses public key to encrypt information to device A. Right. And each device's private key are kept secret. Otherwise, anyone or anything possessing them will be able to decrypt the information and view the information. So in order to get to the asymmetric cryptography, RSA is the only practical algorithm which is available today, and also the integer factorization cryptography algorithm. So this is practical for encrypting and decrypting small amounts of data up to the modulus size like 1024, 2048 in use. So that's why, like, you cannot encrypt a large amount of information. So what generally we use this thing, let's go over through the advantages. Like only one party possessing the pairwise RSA private key can decrypt the traffic, which is very big thing. And if you come to think about it, that how it is actually beneficial than symmetric key. So let's say that in symmetric key, if two keys have to share a key, then there has to be a common channel through which the keys are shared. Now, in order to send this information, let's say you make a IoT device in Delhi and another one you make in New York, then how are these two devices going to have a shared key common? You have to transfer it, and when you transfer the shared key again, the whole issue starts to happen again. That how to transfer it wirelessly. So now with this what happens is that I will create a public key and private key, and I will keep my private key, and I will release my public key to a certification authority. Now, certification authority is the one person who the entire network trusts, and if you have to fetch a public key from anywhere, you fetch it from a certification authority. So now, if let's say the device which is there in New York wants to send information to the device in New Delhi, then it will fetch the public key of that device from the certification authority, and then it will encrypt the packet, which only the device at New Delhi can decrypt. So now, since only a limited modulus size is available, so therefore it is primarily used for key transport. So first, using RSA, we do a key transport and we establish a session key. Once that session key is established, then the transport symmetric keys or random values used as precursors to cryptographic keys, they take over from that point onwards. So as an example, a very important example to follow along. So let's say there is a TLS client server protocol which uses RSA cipher suite to encrypt. Now RSAs encrypt the clients, this client who is sending the information pre-master secret with the server's public RSA key, and server's public key, which is usually present and embedded in an X509 certificate, is available. So that is like, in this I'm trying to explain how this key transport is taking place. So we have a pre-master secret, which PMS key, which is usually called the PMS key, and that we're trying to encrypt with the public RSA key of the server, which we are getting from the X509 certificate, which the server is having. It's coming from a certification authority basically. Now, after sending the encrypted this PMS to server, both sides have the same copy of the PMS, and now there is a session symmetry key which is established, and can be, the entire thing can take place through the symmetry key, which is more simpler to implement. The other one which we discussed about, IFC, the integer factorization cryptography using RSA, has certain security concerns as advances in large number of factorization techniques and increased computing power. So, best recommendation is to actually use larger or RSA modular size like 2048 bit to establish that session key and then do the communication. So that is it for this video, and we'll thank you.